Okay. Hello, everyone. I'm Renee Yager, the Director of Marketing at EPC, and welcome to today's webinar, using test-to-fail methodology to accurately predict projected lifetime of GaN FETs and ICs in common DC-DC converter topologies. This is the second of our four-part summer series, which is running bi-weekly through the end of August and focusing on GaN reliability in real-world applications. If you missed the first installment, which was focused on solar applications, the replay is available on the website at epc-co.com. Remember that you can earn reward points for registering, attending, and engaging, and be entered in a raffle to win a $2,500 Amazon gift card. The details of the awards program are also available on the website. So before we get started, just a couple of housekeeping items. You do have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. You can send your questions in at any time. We'll collect these and address them during the Q&A session at the end of today's presentation. Now, I would like to introduce our speaker today. Dr. Shankye Jong is Vice President of Product Reliability at EPC, where he leads the conduction of failure analysis for all GaN transistors and ICs. Prior to joining EPC, he worked as Senior Failure Analysis Engineer on RF MEMS devices in the mobile industry. He earned his PhD degree in Material Science and Engineering from Arizona State University, investigating low-loss dielectrics for cellular and advanced computing applications. He is the author and co-author of more than 20 technical papers, a committee member and our internal liaison for JEDEC's JC70 Wide Bandgap Power Electronic Conversion Semiconductor Committee. Shankye, thank you for joining us today.
All right, thank you. So let's get started. Today, we will discuss using test-to-fail methodology to accurately predict projected lifetime of eGaN devices in common DC-DC converter topology. Why test-to-fail? Standard qualification typically produce zero failure out of a large group of parts tested. Therefore, it's quite challenging to apply the test results to a specific application that has a unique mission profile. That is why we need test to fail and follow with failure analysis to understand the underlying failure mechanisms. Here is a list of stressors and the corresponding intrinsic wear-out mechanisms. The detailed methodology and the result were published in this peer-reviewed book, the GaN power devices and the application. So here is a 48 volt to 12 volt buck converter developed by EPC, featuring EPC 2218, a 100 volt rated eGaN transistor. As you can see in the efficiency plot on the right, 100 volt rated eGaN devices offer superior efficiency at 96.5% with 48 volt input and 12 volt output at 50 kilohertz. So here shows a 48 volt, 1 kilowatt LLC resonant converter developed by EPC, also featuring EPC 2218, a 100 volt part on the primary side, and 40 volt EPC 2024 devices on the secondary side. Low voltage eGaN devices offer 97.5% of peak efficiency at 400 watt. For DC-DC converters, we identified three main stressors, which are gate bias, drain bias, and temperature cycling, TC. All three stressors are critical and affect the total lifetime. So the question is, how can we quantify the impact of each stressor towards the total lifetime? We developed this equation to quantify the influence of each stressor. Basically, the harshest stressor, or the one that give you the least lifetime, dominates the overall lifetime. So next, we will examine each stressor individually. Gate bias. To start off, let's look at our gate structure in this TEM cross-section image, where we can see the source metal, gate metal, source field plate, and the gate. You may notice a dark layer between the source metal field plate and the gate. This is a silicon nitride dielectric layer. Please keep this cross-section in mind because we will come back to this image when discussing gate failure mechanism. We conducted accelerated gate reliability testing, where we took our devices well beyond the datasheet limit and monitor how they fail. Here is the Weibull distribution plot of the test results, where the vertical axis is the failure rate and the horizontal axis shows the time of failure in unit of seconds. We took 4 group of parts, 32 devices each group, and tested them at 8 volt, 8.5 volt, 9 volt, and 9.5 volt, respectively. As you can see in the Weibull, the devices fail very quickly at 9.5 volt, but it took hundreds of hours to generate just 2 failures at 8 volt. After failures were identified, we conducted failure analysis. Now let's take a look at our FA results. So here's the cross section of the failure site, where you can see the failure occurred between the gate metal and the metal 1 field plate, as shown in this circle. In fact, all the devices failed in a similar manner, sometime on the left, sometime on the right. So based on the FA result, a good understanding of the intrinsic wear out mechanism was found. So next, we would like to use a physics-based model to explain this failure mechanism. So we are going to use impact ionization process to explain the failure process. In the first step, electrons are injected into the p-GaN gate layer from the 2-dep over the aluminum gallium nitride barrier layer, as you can see that right here. In the second step, where electrons enter the p-GaN gate and they are accelerated rapidly by the electric field, with some gaining sufficient energy to cause impact ionization and generate holes. In the final step, holes are trying to move away from the gate corner under the influence of the electric field and become trapped in the silicon nitride dielectric layer, leading to a growing positive trapped charges, QH. Once this charge density reaches a critical density, the dielectric ruptures, causing the catastrophic failure mode at the gate corner, as observed in failure analysis. So this slide shows how we model this impact ionization process. We follow peer-reviewed publications summarized in this table. By combining various equations, it yielded our final expression for the mean time to fail responsible for the gate failure. Now let's take a look how well this model explains the experimental data. The impact ionization model is plotted against the measured data points for EPC 2212, where a good fit is found. If we keep the gate bias at 6 volt, the VDS max, we project less than 1 ppm failure rate over 35 years of lifetime under continuous DC bias. This projection is also consistent with our field experience. Next, drain bias. To start off, let's take a look at the cross section again, where we can see drain contact, field plate, gate, and source contact shown in the image. First, we would like to examine the physics that of RDS on shift. So when devices are subjected to high drain bias, we observed a lot of hotspots using EMI, a common failure analysis technique. Those hotspots suggest that electrons were accelerated by the high electric field and become hot carriers. If we zoom in the hotspot image and overlay it with the mask layout, we found that the hotspot predominantly occurred at the edge of the drain contact, as shown in this picture, indicating that where that is exactly where the electrons got trapped and therefore responsible for the dynamic RDS shift. By using this imaging tool, we designed our generation 5 and generation 6 devices that are much less susceptible to hot carrier injection induced dynamic radiation shift. Based on all the findings discussed, we developed a physics-based model to explain this hot carrier trapping process. So electrons in the 2-DUG are accelerated by the high electric field and then scattered by the lattice and become trapped in the passivation film by the drain contact where those hot spots were seen. Now we align band structure near the drain contact where we can see an energy barrier that exists for the electron to overcome. The majority of electrons do not have sufficient kinetic energy to get over the barrier. Only a very small fraction of electrons does, then subsequently get trapped within the silicon nitride dielectric layer. As more and more electrons are trapped, the barrier height is further enhanced by the electrostatic field resulting from the trapped charges, as indicated by this arrow. This dynamic barrier height change is essentially the key for the lifetime model development. Here are the equations we used to model this hot carrier trapping process. By combining everything together, it yielded this final dynamic RDS equation that includes voltage, temperature, and time. Now let's take a look how well the model fits the experimental data. Here shows a comparison of measurement and model for EPC 2045 100 volt generation 5 devices operated at 4 different voltages and 3 different temperatures. Good agreements between measurements and model were found, which demonstrate the validity of the model. So after we have a model, now let's apply the model we developed to project lifetime for a buck converter as an example. Here is a common 48 volt to 12 volt buck converter operating in continuous conduction mode. All parasitic inductance were added in the schematics. Now we introduce 200 picofarad L5 parasitic inductance to simulate a worst case scenario in application. So in SPICE modeling, we observe a peak voltage ring of 120 volt approximately with bus voltage at 80 volt during turnoff. So this waveform basically is potentially the worst case scenario in real world application. Now let's examine how our using a reliability test to fail approach, how will we do in this under these stress conditions? So here shows the turn off voltage waveform again of the buck converter shown previously, where you probably noticed the key stressor is the over voltage ring. Let's first focus the first 3 rings with the highest amplitude, which I believe to have the most impact on GaN reliability. Here's the zooming image of the first 3 rings. So we found that the over voltage ring can be deconvoluted by individual sinusoidal shape voltage spikes, as shown in the red curve right here. Okay, so now the next step to emulate the over voltage ring effect. So we developed this unclamped inductive switching test circuit, as shown in this schematics recently, where we can also conduct in situ RDS monitoring to monitor how well how the RDS change over time under this 120 volt repetitive over voltage spikes. On the right is the resulting 120 volt peak over voltage waveform that is produced by this unclamped inductive switching circuit. Therefore, the deconvoluted over voltage ring can be simulated by this UIS test circuit. So now let's examine how well our GaN FETs performed on the repetitive 120 volt over voltage testing. Okay, So here's the test results. We tested 3 representative EPC 2218 100-volt rated GaN FETs from 3 different lots and wafers to 1.5 billion of 120 volt over voltage spikes, where very minimum radiation shift was observed. When we project the shift to 25 years using the lifetime model we developed using the hot carrier trapping effect, we observed that all the data points collected by the UIN, the unclaimed inductive switching circuit, fall exactly on the projected line, and the projected shift for 25 years is less than 10%. Now let's test our latest PQFM device, EPC2302. So we showed 1 representative EPC2302 device, also 100-volt rated, to a whopping 10 billion cycles of 120 volt over voltage spikes, where very small radiation shift were measured. So as you can see, the additional 8.5 billion switching cycles still follow the linear projected line, which provides further validation to our hot carrier trapping lifetime model developed. It also shows that very small radiation shift over 25 years of continuous operation under repetitive over voltage switching. So the collective results demonstrate the extreme robustness of our 100-volt GaN FETs on the 120-volt over voltage repetitive switching. Okay, so next, as you can see that let's come back to this turn off voltage waveform from the buck converter, where you notice that there's another critical component of this voltage waveform come from the 80-volt bus voltage. So therefore we can also deconvolute this 80-volt bus voltage by using a resistive load hard switching circuit to emulate the stress condition. Here shows the turn off voltage, drain voltage waveform collected by our resistive load hard switching circuit and overlay it with the buck converter turn off waveform. So here is the resistive load testing circuit. Here shows the schematics we developed to model the hard switching turn off characteristics, where we can also monitor the evolution RDSO in situ at 100 kilohertz. So the drain voltage turn off waveform is showing on the right. So here we tested another representative of EPC 2218 and EPC 2302, both 100-volt rated eGaN transistors. One 2218 is the chip scale package part. EPC 2302 is a package QFN package devices. So both devices we found less than 10% radiation shift over 25 years of continuous operation at 80 volt and 100 kilohertz. This also demonstrates the robustness of our 100-volt eGaN FET under 80-volt off-state bias. So next and lastly is the temperature cycling, TC. Board level temperature cycling testing of EPC 2218 was done at 2 different conditions, which are minus 40 C to 125 C and minus 40 C to 105 C. At TC1 condition, we tested 2 groups of parts with and without underfill devices, without underfill material. We generated another viable plot for 3 sets of temperature cycling data using our test-to-fill approach. Most importantly, underfill drastically improved the temperature cycling reliability of our chip scale package devices. As you can see on the right, the black curve on the right, we have yet identified any failure to date at 3,000 cycles of minus 40 Celsius to 125 Celsius testing. Based on this test to fail and viable data, now we are able to develop a general temperature cycle lifetime model as shown here, which is known as the Noyes-Landsberg model. So N on the left is number of cycles to failure. A is a coefficient. The first term is a frequency term, which includes how many cycles per day during this temperature cycle testing. The second term is the delta T term, which is the classic Coffin-Manson equation. This term focuses on the solid joint fatigue wear out mechanism. Lastly is the Arrhenius term, which is primarily to model solid creep wear out mechanism, because solid typically fails faster when the hot extreme temperature is higher, which is Tmax is higher. So here are the parameters for the lifetime model of EPC 2218 using SEC305 solid material. Okay, the next question, so we have this lifetime model. How do we use it? And then how can we apply the model to project lifetime in real world application? So let's first start with this Noyes-Landsberg equation, TC lifetime model again. First, let's assume the Tmax is 125C, possibly the worst case scenario in application. So therefore, the Arrhenius term essentially is a constant, a coefficient. We can lump it into a coefficient. Now we can plot the N on left side of the equation, cycle to failure, as a function of delta T at 100 ppm or 0.01% failure rate. We collected from the test to fail viable plot. Okay, so let's take a look. Here's the result. So by assuming the Tmax 125C, we are plotting basically the classic Coffin-Manson equation, and as a function of delta T at 100 ppm failure rate. Now let's look at, and let's come back to this the temperature cycle lifetime equation again. Now let's assume Tmax is only 100C, which is less than the previous case. So based on the understanding of the underlying failure mechanism, we ought to have slightly longer lifetime, right? So now let's plot N as a function delta T again by assuming Tmax is 100 Celsius, 25 degrees less than the previous slide at 100 ppm, 0.01% failure rate. Here's the result, where we see slightly improved lifetime compared to Tmax of 125C. Now let's take a look. We add Tmax of 75C and Tmax of 50 Celsius, and then we plot them on the same plot as showing on the right. So as you can see, makes sense. As Tmax decreases, we got more and more lifetime. So now the question is how to read this plot if the engineer who is playing a DC-DC converter. So how can we use this plot? So now I'm going to give you an example to show you how to use this, I'll say empirical equation generated plot. First, let's assume now it's basically the summer in Phoenix, Arizona, where the ambient temperature outside, let's say, is probably roughly, in the worst case, is 50 Celsius, which is focusing in the US, is about 122 Fahrenheit. So now, so in outside, there's an application where the DC-DC converter generates another 50 Celsius resulting from self-heating. That's another 50 degrees Celsius. So now, by combining them together, our Tmax is 100C. The delta T is 50C. Okay, now let's come back to the plot on the right, where we can follow the orange curve, where Tmax is 100 Celsius. And then let's read from the horizontal axis with delta T of 50 Celsius, which is right here. Now we can read on the vertical axis, which is cycles to failure, about 20,000 cycles with 100 ppm failure rate. So this just gives you an example how to use our reliability testing result, test to fail, to come to walk you through to a real world application lifetime estimation. Okay, so conclusions. So we have discussed gate, drain, and temperature cycling, 3 reliability stressors. On gate reliability, gate should have very low failure rate when we keep the gate bias at and below the max rated gate voltage per data sheet. On the unclamped inductive switching testing result, we show that GaN devices have extreme robustness under 120 volt drain over voltage spikes. We tested up to 10 billion switching cycles on our 100 volt eGaN devices. Next, using our resistive load hard switching circuit, we found that GaN devices are projected to have less than 10% shift over 25 years of continuous operation at 80 volt bus voltage and 100 kilohertz. Next, in our temperature cycling section, we showed that underfilled chip scale package GaN devices showed excellent temperature cycling reliability. And so based on the test to fail lifetime equation, we developed a methodology to estimate TC lifetime in a real world application. These temperature cycling models can also be adapted to various die size and configurations. So that concludes today's webinar. Thank you. So any questions?
Lost my mute button. Okay. So now we will start answering the questions that came in during the presentation. You can still continue to put questions into the Q&A box, and we will get to as many of them as we can. So first we have on page 10, was the failure always on the left side?
No. So we actually conducted a lot of failure analysis on a lot of failures. So as mentioned in the slides, so sometime on the left, sometime on the right, but it's always on the corner. That's one of the critical findings when we developing the lifetime model.
Okay. Also on page 10, is the silicon nitride material properties consistent among wafers?
Yes. So we actually have a PCM or a lot of test structures on the wafer. We test regularly. They have very good quality. So we test them to fail the test structures. They are reaching the breakdown voltage reported by the literature. So basically they shouldn't break until 100 volt.
Okay. On slide 15, what tool did you use to simulate the hotspots?
It's a EMI. It's basically using it's hot care. It's basically an electron. So it is electron emission, which is a very very standard failure analysis tool. So the detector we are using, I think it's an in-gas detector, and I think that's what we used.
Okay. Can your model be applied to other material systems?
Well, can you say which material system? Can you repeat that question?
Can your model apply to other material systems?
Other material systems. Which model? I'm not quite sure. There's the 3 models we discussed.
Okay, so if you ask that question, could you just send in a clarification, and we'll come back. We'll circle back around to it.
Okay.
Okay. Which current sensor is suitable for GaN-based synchronous buck converters, and why?
I think that's probably Andrea question. Andrea?
Yes, I'm sorry, I forgot to introduce Andrea.
Yeah.
Andrea Gorgerino is also on the panel. He is head of our FAE team. So go ahead, Andrea.
Yeah, I mean, this is a very generic question. I think there are no inherent limitations. You know, it's more of a topology-driven choice. There are things to be careful, of course, and one of them being the fact that your switch nodes usually have higher DVDTs than a silicon MOSFET equivalent design. And so depending on the current sensor you choose, that might be a limitation in the circuit to implement it. Also, if you're using shunts, especially if you put them in series with the FETs, there needs to be some care in making sure they don't couple through the gate driver. So those are some of the limitations in the implementation of some current sensors. But in general, it's a topology-driven topic.
I think this is probably another applications questions. Can GaN devices run directly from controller through isolations without using gate driver?
Again, it's not really a specific GaN topic. If your controller can provide the correct voltages and the correct currents to do it, the answer is yes. Also, it's topology driven. So we have examples, for example, where we do drive our FETs without a specific gate driver directly from a controller. We usually do that on the very, very small FETs. These are really, really tiny FETs. The advantage of GaN is that the gate charge is very small, so that reduces the requirement in terms of current versus silicon MOSFET. But for example, we do that on some topology, which are low side only, so they don't require isolation or level shifting of the signals. That's where a gate driver pretty much becomes required. But yeah, I think basically the gate charge is very small. So if you have a topology that's compatible and you have a good enough controller, yes, and we do that in some of our references and for wireless power, for example.
On slide 26, is the clipped circuit integrated to the EPC FET driver?
No, it's external. So we discussed that. No, it's not.
Okay. Do you have results of dynamic RDS(on) over longer times, for example, 4,000 hours?
We don't have 4,000 hours, but we do have 1,000 hours data that is documented in our phase real report. So basically, they still follow the same trajectory based on model fit by our model.
Okay. On slide 30, can the equation be used for pulse operation?
Pulse operation, TC. So I think so. I think pulse operation essentially the self-heating. We call it the IOL. This is by self-heating. I think so.
Okay. You talked about positive overvoltage. What about negative overvoltage, such as when gate voltage goes below -3 volts due to ringing?
We have conducted a lot of testing on the negative gate voltage. So the answer is there. Our GaN device is not going to fail catastrophically under the top of -10 volts because we actually did all the work and the study on that so gate negative overvoltage. So from the reliability point of view, so under negative gate voltage, we're actually depleting the 2DAC. So we see no hotspot. And also, we conduct a lot of reliability testing. Basically, I don't see failure at the -15 volt. But there's might be some slight parametric shift when you subject the part to that extreme negative gate bias. But if you say -3 volt, I don't see any issue, both from physics point of view and also from reliability testing point of the data point of view. Yeah.
Okay. Is Tmax the junction temperature or a case temperature?
So I think it's the it depends. So okay, if we just talk about temperature cycling, which is resulting from the ambient, that's the ambient temperature. So because under that, so essentially it's the case and the junction, because there's no electrical bias. But if you talk about the say power switching cycles, I think that essentially is the junction temperature.
What is the electrical signature for the gate corner dielectric charging? Is there a change in device BT or other characteristics?
So say this guy after the fact, we caused this failure. So what we're going to observe, we have done a lot of failure analysis, both electrically and physically. So what you will see essentially is a gate to source short. However, the underlying we call channel is mostly intact. So a lot of times, essentially, we are looking at a drain. So it's you are tied the gate and source together. And so drain is not really compromised. You are essentially looking at a diode configuration. So that's kind of the electrical signature post this failure mode.
What type of underfill for the GaN devices have you used?
So historically, we have used Namix and Henkel underfills, which where the data shows they have very comparable temperature cycling reliability. So we actually run a lot of both experiment and finite element analysis. So and generated some guidelines that is documented in our phase real report. Yeah.
What about pulse drain current? From the data sheet, the pulse drain current rating is lower than that of an equivalent MOSFET.
Andrea, can you just say, do you have any thought on this question? Because I'm not quite.
I think it depends really how you do the comparison. I'm a little bit surprised about this, but anyway, the pulse drain current is a measurement of the saturation of the device. It depends what you compare apples to apples. I think it's very equivalent and the mechanism is very similar. Yeah, I think it depends which device you really compare. But on the pulse rating is basically just saturation of the device. I don't think that's very different, honestly.
Typically, GaN should be more intrinsically is more robust in terms because it can withstand more heat and higher temperature. So I'm a little surprised. So that's something we need to look into more.
Okay. Can the MTTF model be applied to other materials like gallium arsenide, for example?
I think that reliability, the general guideline of equations, I think the answer is yes. But the specific failure mode and mechanism probably is pretty unique to GaN. But the methodology and the MTTF equation that should apply to all the devices.
What kind of considerations should we take while paralleling EPC GaN devices? Probably an Andrea question.
I'm very quick. We do have some app notes that talk about it. Again, in general, there are, I would say when you parallel devices, there are current sharing is basically what you are interested in. Current sharing can happen in continuous mode, so when both devices are on, but it can also happen when they are switching. And so you have to care about different considerations. So in the steady state mode, I think it's really about the RDS on, similar to a silicon MOSFET. We both of these devices have a positive temperature coefficient, so that leads to a balancing out of the currents in when they're both on. And during the transient, I think GaN behaves a little bit better than a silicon MOSFET. The threshold is almost flat, while the threshold is a negative temperature coefficient, which leads to unbalance during transients. And during transient, what really matters beyond the device itself is the PCB layout. And so balancing all the layouts and all the parasitics, that's where we have some guidelines, especially with GaN devices. If you want to switch fast, even small unbalances can lead to very bad current sharing during switching events. So yeah, you have to be careful. But the layouts, we basically for high switching speeds, we propose a layout where you parallel the half bridges instead of the actual devices. We have examples of layout. Like again, there's an app note describing that, as well as a couple of reference design that implement that paralleling concept to keep the paths symmetrical as possible. And the other thing that really is recommended is use individual gate resistors to avoid ringing between the two gates. And yeah, I think those are the main things for paralleling, but they parallel very well.
What is the gate delta voltage between the most optimum switching performance and the voltage where mean time between failure starts decreasing?
We recommend 5 volts
5 volts
operation.
Yeah.
5.2 volts.
Okay. Is there any benefit of using a negative output gate drive DC-DC?
No,
Okay.
no, there isn't. You basically, but the implementation of negative gate drive is required when you want to avoid basically self-turn on Miller shoot through type of situations. We are able to avoid that thanks to basically the charge ratios between CGD and CGS. There's on our website, there's some more details, but basically our charge ratio is always below 1. So basically it's very immune to self-turn on. And also the reason you want to avoid using negative turn on is because during the dead time, the reverse conduction voltage drop is actually, although it looks like a diode, it's a slightly different mechanism. And so the voltage drop is higher. And if you use negative drive, it becomes that negative voltage gets added to that voltage drop during the dead time, which will add to dead time losses. So basically it's not needed to avoid the shoot through, and it's detrimental in terms of losses. So we all of our designs and all of our reference designs always implement 0 voltage turn on, which also makes a turn off, which also makes the gate driver easier.
Are there accelerated combined effects when both gate and drain are stressed together, or does the simple addition of MTTF, as you showed in the beginning, agree with experimental data?
Yeah, I think this is okay. Let me first explain. So how we come up with this equation. So this I listed the literature that how we come to this equation essentially based on the failure rate. So when you have different failure mechanism, the total failure rate is the sum, is a simple summation of all the ones that are included. So because failure rate is proportional to 1 over mean time to fail. So that's how we develop this equation based on literature. So if we take the mean time to fail and together, so what we have learned is that the gate is not really a problem. So it's so basically from the denominator point of view, I think probably so far we are looking at drain. I don't think the intrinsic from the intrinsic wear mechanism point of view. First, there's no catastrophic failure, even to 120 volt over voltage switching. And then I don't see there's anything, there's the mean time to fail is very little, basically. So that leaves us the last term, which is temperature cycling. So for our chip-scale package part, I think probably temperature cycling, depending on mission profile, that could be a limiting factor. But by adding underfill material, that should solve the problem. So this is showing approach, how we try to address the reliability issues. So when we see something that is, we have a very significant denominator, which is temperature cycling in the beginning. That's why we address it by using underfill material. So far, I think the total, the mean time to fail or the fail rate over in the field is consistent with this, with what we have studied based on our reliability testing results, which is very low.
What will be the effect on dead time if we consider it for a synchronous buck converter as compared to IGBT or MOSFET?
Well, the effect of dead time is that on a GaN device is if you at the end of dead time is required because of rise and fall time. So those are much smaller in a GaN FET than a silicon MOSFET or in even IGBT even more. Also, there's no reverse recovery. So at the end of the day, in your application, regardless of the topology, you can operate with very short dead times. We typically operate our FETs in our reference designs below 20 nanoseconds dead time. In a regular buck converter, maybe it's not a huge impact. In some corner cases, it can be, because basically you have more volt seconds available, or basically you can operate in some more extreme duty cycle operation corners, which might be beneficial depending on your particular application. In other applications, it's even more beneficial, like in motor drives. It reduces a lot of the distortions of modulations. So basically the effect of the dead time is topology specific, application specific. The advantage of GaN is can operate with extremely low dead times.
How can the test to fail approach effectively account for various stressors and interactions between device components, such as parasitics, thermal effects, and electrical overstress?
That's exactly what we discussed today, right? So that's say just one example. We have the over voltage stress. I think that's the last thing mentioned. That's which we can deconvolute by looking at this turn-on waveform in application. That's how we address the. So basically, we use the piecewise approach. We deconvolute each stressors to a standalone that can be modeled and studied in the reliability lab. Then we design a representative circuit and topology to emulate the stressor. Let's just use over voltage as an example. So this is how we do it. And then we test it repetitively. We test different wafers, different parts, different at different time, 1.5 billion, and then to 10 billion switching cycles. Essentially, the goal is to understand the underlying failure mechanism. So we don't have to test, say, 4,000 hours. We just need to test, say, 2 hours. So and then everything else agrees. So basically, we test for 2 hours now. We can project what's going to happen at 25 years by understanding the underlying failure mechanism. That's why we spend so much effort in failure analysis and the model development. And then all the data we are taking are following exactly on the projected line, and then we show the validity of our model. That's kind of the approach we are. That's exactly the approach we are taking to address the reliability concern. So what was that? I think, am I answering that question?
So you mentioned Gen 5 and 6 improvements in the drain stress fail reduction. Is there a die size cost for this?
No, we are. So what we are doing is that we actually just take this cross-section image. So the answer is no. So we actually improve the die size or reduce the die size by shortening the distance between drain and gate in our Gen 5 and Gen 6. Gen 6 is further 20% reduction in terms of die size, which give you same performance. So, but one of the critical concerns is dynamic RDS(on). But we have this approach, and then also with some TCAS simulation, we can effectively modulate the electric field, so that to mitigate the RDS(on) shift effect. So with the combination of understanding the physics mechanism, and we have a very surgical and a sensitive tool to image, and then we have that can be validated by our simulation and then our DOE experiment. So that's kind of the approach that we are taking to develop our Generation 5 and Generation 6. The short answer is no. So we actually shrink more in Generation 5 weeks. So basically we're getting better performance devices with less die size.
Okay. Have you compared the test to failure for GaN on silicon versus GaN on GaN, GaN on silicon carbide?
No.
Do you recommend the use of additional overcurrent protection when using your ICs?
That is application specific. Our IC don't have overcurrent built in. So if your application requires some sort of overcurrent protection, then you will have to implement it separately. Yes.
Cool. All right, great. So I think we got to most everybody. So I just wanted to say thank you, Shanky. Thank you, Andrea. Thank you to everybody for attending today. If you do have any additional questions, you can send them into info@epc-co.com and we'll get them answered for you. You should get an email in the next 24 to 48 hours with a link to view a recording of today's webinar, as well as a copy of the presentation. Lastly, be sure to register and attend the remaining installments of the Summer of GaN webinar series. The next one will be in another 2 weeks on August 9th. We'll be talking about reliability in space applications. You can visit us at epc-co.com for more information and to register. Thank you for joining us today and have a great rest of your day. Thanks, everybody.
Thank you.